Yeah, dear students, today we will discuss BTREES. So, before starting BTREES, B stands for is nothing but balance trees. Okay, B stands for balance trees actually. So, as we have discussed in the last class, that in binary search tree, when the nodes that are being inserted into the binary search tree are going in a skew order, either left skew or right skew, uh, the amount of time complexity to search in a worst scenario will be polynomial. In order to reduce this complexity to logarithmic, what we did, we had gone for AVL tree, right? AVL tree is also what is a kind of balanced binary search tree, yes or no? So invented by Anderson, Wilsky, and Landis. So here, similarly, B tree is also one kind of balance tree here. The idea behind balanced B tree is, to insert more than one keys at a node. Like in binary search tree, you will be having only one key, right? And you'll be having two pointers, left and right. Left pointer will hold the address of the left node, and right pointer will hold the address of the right node. Yes or no? So that way, it goes like this. Fine. Yes or no? So, if I insert more than one key, what happens? See, instead of a single key at every node, if we are inserting more than one key, okay, like you have a pointer to point to, you know, child, leftmost child, then I can have one node and then one pointer to this 10, and one node and one key and then pointer to this key, one key and pointer to this key, something like this. When I have more than one keys over a single node, then what happens? The depth of the tree will be reduced. When the depth is reduced, the automatically searching time complexity will also be reduced. So that way also you can probably reduce the time complexity by converting the binary search tree into the balanced trees, right? B tree kind of thing, right? By increasing the number of keys at every node, thereby decreasing the depth of the tree, rather, right? This is what exactly the motivation behind BTREES. That's what exactly that what I have discussed. We can just have a glance over this, PPT. So far, what we have assumed is nothing but entire data structure in memory to be stored, right? So, what if we store, data which does not fit, rather, right? So, our main idea is to reduce the time complexity, rather, right? So, by because you can look at you can see here on the hard disk basically the rotations per minute, the time complexity that you basically measure in terms of RPMs, right? When you are switching it from the external memory only, the issue is basically is resulted with, rather, right? So since you have a lot of data in hard disk, your head has to move across all such kind of elements across that cylinders, which takes good amount of time. In order to reduce that time, what we are trying to do, we are trying to make our data structure to be an efficient, so that the time complexity across our data structure once we reach there should result in a less time, rather, right? This is what exactly our motivation behind going for this particular B tree. So now if you look at the properties of B trees, we can say B tree is uh, of order sum, of order m, if I say, probably, right? If I take a B tree of order m, then I call it as a M-way tree, rather, right? So, or emery tree we call it as, rather, right? You may have heard about two to three trees. This is also a kind of B tree itself, right? Where you have two keys and three children, rather, right? So, or 4-5 tree, right? 4-5 tree is also a B tree, right? Where you have four keys and five children, rather, right? Keys and children's. Okay, so when you can see, this is the property of BT when applied with the varying number of keys. These trees are going to be formed, like 2 to 3, 4 to 5 kind of thing rather, right? Or emery trees or MV trees rather, right? So here, when I say M way tree, it means you will be having M children. M children in the sense that like for example, binary search tree. When you take, in binary search tree, how many children will be there? Two children, left child and right child, right? That's how it is a binary tree. We said there are two childs. But if you have M children, then we say it is a M way tree rather, right? So in M tree, you will be having M children. When you have in binary search tree, when you have two children, how many keys will be there? One key, right? Yes or no? Only one key. So it means keys will always be one less than the number of children. So similarly, if you have M children, it means that number of keys available in the M tree will be M minus one keys, right? This is the first and foremost property of the B tree, right? So of order M. When a B tree of order M has to be defined, it is nothing but it will consist of M children and M minus one key, right? So now looking at the different properties here that are listed out, the number of keys in each non-leaf node is one less than the number of its children, right? So always the keys are going to be one less than its children, right? And these keys partition the keys in the children in the fashion of a search tree, rather, right? So they have to be, as I said, should be stored in such a way that the child of right child of 10 should carry the values more than 10, but if you have next to 10 is 20, then it should be less than 20, because this particular child becomes the left of right 20 and right of 10. It means that this particular node, the key value that this particular node will have is more than 10 and less than 20. So this is how exactly in a such order kind the elements have to be rather stored. All leaf are on the same level. So in B tree you find all the leaf nodes are on the same level. This is another property, right? And all non-leaf nodes except the root have at least m by 2 children. So if a children which is a non-leaf, in between you have rather, right? If you have a, we'll see probably with the help of demonstration, fine. So this particular tree, this particular node should have m by 2 children, minimum of m by 2 and maximum of how many? M, obviously, rather, right? If it is a m by tree, right? Because basically any B tree is going to be defined with the help of an order. Order must be, if I am saying, let us say m, then maximum number of child that it can has is mem, and minimum number of children that it can have is m by 2 rather, right? The root is either a leaf node, generally the root, this root, which is on the top rather, right? If you have only one node, that itself the leaf node, it means the root node itself is the leaf node rather, right? Or it has two or more m child. So for root, exception is given that it can have minimum of two child as well, right? Got it? Root, only root. Root can have minimum of two child, and what could be the maximum that a that a root will have? Of course, m child, right? But for all non-leaf nodes, except the root, you will find that the minimum number of child it should have is minimum is m by 2 and maximum is m rather, right? A leaf node contains no more than m minus 1 keys, right? At the end, the last level, the level at which you have the leaf nodes, if you see, each node cannot have more than m minus 1 because the order is m. When the order is m, you can have how many maximum of keys that can be available in a particular node? It should be one less than the order rather. It means m minus 1. So m minus 1 keys, maximum of how many keys that any node can have is m minus 1 keys, and maximum of child is going to be m child, right? So these are the properties. So based on these properties, the b trees are going to be constructed. Now we'll probably see how we will be inserting the nodes when the data is given to us in order to construct the BT and delete from the same gather, right? And what are the cases, extreme cases that you may encounter with while you are inserting and deleting, and how you are going to solve the same. Let us look at an example of a B tree where you can see 26 is the root. If you see here, 26, right? So if you see 26 is root. A root, as I said, it can have minimum of two child. You can see there's a left child and the right child. What is the order? Order is given as 5. It means m value is, what is m value? That is 5. So obviously, the maximum number of child that any leaf node can have is about m, right? A non-leaf node except the root. Okay, and minimum number of keys, minimum number of child that any number, any non-leaf or any non-leaf node except the root is m by 2. Okay, and as I said, a root can have what could be the minimum number of child, two child, and maximum number of child that it can has is m, right? If the order is m. Okay, similarly, if you are probably looking at the keys, keys minimum could be 1, right? Minimum could be 1 for root, and maximum could be m minus 1, obviously. Yes or no? Fine. So you can see here root is 26 here, and it is having left child in left child consists of 6 and 12. So left child values, the entire left subtree must be values carrying less than 26, right? This is similar to BST kind of property that BT has to satisfy, right? The left subtree values always should have the less than the root, and right side value should always be greater than the root, rather, right? So to 26, right, if you probably see, they are all greater. Yes or no? 42, 51, 60, they're all greater, you can find, right? So similarly, this is one intermediary, this is another level. Okay, so at this level, if you probably see, right, you can find the maximum number of child that you can have is m, and minimum number of child that it can have is m by 2. M by 2 in the sense 5 by 2 means two child. You can see here m by 2 plus 1 is going to be 3 child, right? One, two, three. If I take the floor m by 2 in the sense, I need to take the floor. Yeah, if I take the value of when it is odd, basically, when it is odd, you will have two options. You can go for roof or floor, rather, right? So which one you go with? You go with roof. Okay, the highest one. Fine. And so you can see here the non-leaf node 6 and 12 is carrying three child. Okay, this is one child, and this child is left of 6, and this child is right of 6, left of 12, and this child is right of 12. So you can see this child must have values all less than the 6, and this must have values greater than 6 and less than 12, and this must be greater than 12 because they are all they are all right to 12, rather, right? So similarly here, if you look at, this is on the same level, this is on the same level, right? This is one node. Because of space constraint, he has written here. So another node that you have for the root, the right child, is carrying again three values: 42, 51, 62. So the left of 42 should be less than 42, and it should be greater than 26 at the same time, right? And to the right of 42, you have this, which is left of 51 as well. To the right of 51, which is left of 62. So this way, the by satisfying the B-tree properties, the elements have to be placed and then has to be inserted at the same time. The elements have to be created in such a way that they will satisfy all the properties of B-tree at any point of time. You can see the leaf nodes. These are all the leaf nodes. This is the second level. Yes or no? So you can see all the leaf nodes are at the same level, unlike your binary search tree. Fine. So these are all the properties of B-tree that you can see by satisfying all such properties. This particular B-tree is available for us, right? Now, what kind of operation that you can perform over the B-tree are first foremost thing is the search operation. Next is of course the insert and delete operation. In order to perform both insert and delete, you need to perform what? You need to perform the search operation, right? So now look at construction of B tree. So while you are constructing a B tree, there are two possible cases you probably find. Okay, fine. If you are probably, let us say, taking the order as five here, order is five. I'll just write down what root can have what non-root elements, right? What could be the minimum number of child and uh, maximum number of child and minimum number of keys, first you have to write down this, okay? Root and non-root, okay? Because root is a special one, right? For root, minimum number of childs are two, and maximum number of child as per order. What is the order here? Order is five given for us, right? So maximum number of child that it can have is of course five. Minimum keys are going to be one, okay, and maximum keys are going to be two. Yes or no? Sorry, maximum number are going to be four. Maximum number of keys are going to be 4. Similarly, for non-root nodes, minimum number of child that it can have is 3 obviously, and maximum is 5. And minimum number of keys are 2, and maximum number of keys are 4, right? So you have this table available with you. Now, keeping this in view, what you can do is you can, probably start inserting the elements over the B tree. But then before you go for it, there are two cases, as I said, right? You find case one, when you're trying to, first thing what you have to do in order to even insert or delete, you need to first search, right? Search must be done. Search is a prerequisite, you can say, right? So a node which you have identified in which the key can be inserted is a leaf node, is a leaf, and having less than maximum nodes, less than maximum keys, then you can simply insert it because you have a room. Then insert it, right? Because you have a room for a new key. Because a node can have maximum, but you have identified that the node in which you have to insert this particular key is having less than maximum keys, right? Less than maximum keys. It means still there is a room to insert a new key, new element rather, right? So this is one case one. Then case two, okay, that is when the node you have identified, okay, is having minimum keys, is having is having maximum keys, is having maximum keys, is having maximum keys. See, on any node, as per you can see if it is a root or non-root, maximum number of keys that you can have only four, right? But if the node in which you have to insert is already having four keys, then you cannot insert another key, right? In that case, what is the solution? Is you are going to split the node, right? Split the node uh, by sending the middle over the middle key value, middle key to its parent, right? To its parent, in the sense that if say let us say for example whether it can be root or non-root, no issue, right? See, this root is already having 1 to 8 12, fine. When you're inserting here, let us say these are the elements to be inserted: 1 12 8 2 15. This is the order in which you have to insert the element. When you're inserting one, you can comfortably insert in the node by creating a new node as a root, because when there are no nodes, the node which is going to be created is going to be the root node rather, right? So we'll be inserting that one here. Then when you insert 12, 12 also comfortably can be inserted, but while inserting in the same node, they have to be placed in the ascending order, right? That has to be followed. Now when you're inserting 8, 8 also can be comfortably inserted, and 12 also, sorry, 2 can also be comfortably inserted. So till 1, 12, 8, 2, when you insert, you can comfortably insert because you found room or space for the particular keys to insert at that particular node, right? But then when you are trying to insert here, let us say 25, what happens? 25 to insert, the place which you have identified is here, right? But can I insert here? No. Since the number of keys that this particular node is already having four keys, which is nothing but max keys. So as per the BT property, it cannot have more than maximum keys. So it means it is coming under case 2, right? Previous all the elements when you were trying to insert, they were all case 1, right? But now when you're trying to insert 25, that comes under the second case. So in that case, what you're trying to do, you insert first 25 as per the order, then you will split this node into two nodes by sending the middle key value into onto its parent. But there is no parent here because this node itself is a root. Then in such situation, you will create a new node as a root node, and you will send this 8 as 8 to the parent of this, creating that as a root, and then taking the left part of it as one node, which is going to be added as the left subtree to the key that you have sent to its parent, and the right side part will act as a right subtree, uh, right subtree to the key that you have sent to the parent, right? So now you can see this 8 has gone. This was the only node, basically, right? There was no parent to this particular node. In that case, what you're trying to do is you are creating a new node as a root node. Now root has changed, right? Earlier it was this, right? Now you are creating a new node as a root node, and then sending the middle value over that root, and adding these two splitted nodes, left and right, to the left and right pointer of this particular key that you have sent onto the parent, right? This is how you do it, right? I hope this is clear. This is what exactly the mechanism, the only possible two extreme cases that you may encounter with when you are trying to insert any element over the B tree. By following these particular cases, you can comfortably insert, and at the same time you can satisfy all the B tree properties as well. I hope this is clear to all of you, right? So now let us complete this example by checking with all such kind of possible, elements when we were inserting. I hope this is clear.
Yes, sir.
Yeah. So now you can see here, I have 1 to 8, 12. Now I have to insert 25. So as I said, when you are inserting 25, it has to come here. But then if it comes here, what happens? It will become more than max. So in that case, this node is going to be splitted, and you can see 8 is the middle element which will be sent on to its parent, and this this particular node is going to be splitted into two, left and right, and the left part will go as a left link of this middle key value that is sent on to the parent, and the right will go as the right link, right? Since there is no parent, so a new parent is created. You can see therein this particular middle element was placed, that is 8, okay? So now when you're trying to, let us say, insert 6, 14, 28, what happens? Fine. This is your tree. 8 to the left you have 1, 2, and to the right you have 12, 24. But you want to insert 6, 14, 28. So when you are trying to insert 6, when you are trying to insert 6, where does it go? First you need to search. How do you search? Basically you will compare your key to be inserted with the root first element. There is only one element, so when it is compared, it is found to be less, then you go to the left subtree of the same. So when you go to the left subtree of the same, you find 1, 2, so 6 has to be seated to the right of it. You can see this particular node in which you want to insert 6 is having less than the maximum number of key values, so it means it is coming under case 1. So in case 1, what will you do? You simply insert here, right? Creating a separate, a new room for 6 adjacent to 2, and you can insert 6 here. Yes or no? Similarly, for 14, when you're trying to insert 14, what happens? You first compare it with the root, it is greater, so you go to the right. When you go to the right, you already found 12 and 25. This means this particular node is having less than maximum key values. It means you can probably insert 14 here. So when you are inserting 14, you need to create a room for it. Where do you create a room for it? As per the ascending order, this value has to be seated. So it has to be seated after 12. So after 12, you create a room for new value, that is 14, and then you insert. So now your tree becomes 12, 14, 25 here. Similarly, when you are trying to insert 28, it goes to the right, and you can find a new room for 28 here, since this particular node in which you are trying to insert 28 is having less than the maximum key value. Maximum key values allowed are 4, but it's having only 3, so you can still find a room for 28. So creating a new room for it and then inserting. So this is how. So you can see after this particular tree is going to be transformed like this. Okay. Yes, sir. Is it transformed? Yes. So similarly, you are going to insert. Fine. When you want to, let us say, insert 17, 17, where does it go actually? 17 will go 17 will go to the right of 8, but then the node in which the 17 has to be inserted is already having max key values. Yes or no? So if the node which I've identified where this key has to be inserted is already having max key value, then what do? You go with case two. You need to split this right into two by sending the middle value to its parent. So first you make a room for 17. Where does it has to sit? It has to sit here after 14. Yes or no? It has to sit after 14, so you will create a room for it. But then when you see the middle value is 17 itself, so you will send this 17 to its parent. Then you split the left values as its left subtree, right values as its right subtree. So your tree becomes like this. Okay. So you will get 8 and 17. To the left of 17, you get this. At the right of 17, you get like this. Fine. So you can see the effect here. Yes, sir. You can see 870. So these are the only two possible cases with which you can probably comfortably insert all other possible elements. 750 to 1648. When inserting 7 goes to, so you can see all these elements are being added. So you'll get the, when you are trying to insert 68, where does it go? To the last, but then it is already having maximum key. Then this particular node will be split. The middle value will be 48. 48 will be sent on to its parent, and 25, 28 becomes the left of 48, and 52, 68 becomes the right of, you can see exactly, right? So this is how the tree going to be formed while you are inserting the element. So by following these two cases, you can insert comfortably at the same time satisfying the B tree properties rather, right? So when you are trying to add 3 here, what happens? Which node is going to be splitted? The node which I've identified here to insert key value 3 is going to be this one. Yes or no? So 3 is lesser than 8. So you come here, you find 3 to be seated here, but then the node is already having maximum key values. Then in that case, you need to split this, right? So by first inserting 3, it means finding the room for 3. Then you will identify the middle element 3 itself, so it will be sent to its parent. Then this will be splitted into two. Left of this particular node goes to the left of 3, and 6, 7 goes to the right of 3. Like this, the tree is going to be constructed. You can see here. Yes, sir. So I hope this is clear to all of you. This is how you're going to insert all the element. Now let us say when you're trying to insert 45, what happens? When you're trying to insert 45, where does it go? The node in which the 45 has to be inserted is, you first compare your key with the root first element, which is your key is greater than the root first element. Then you move to the next element. which is still greater, go to the next element which is still greater, but when you go to the next it is less. So left of 48 you should go. It means you need to go to left of 48 means this one, right? So this is the node in which you can probably insert 45, but then that node is already having maximum key values. Then what do? You need to split, right? You first identify its space, that is 45. The middle element is 25, so 28 will be sent to its parent. But then when it is sent to its parent, what is happening? This particular node was already having maximum key value. This is also further required to be splitted, right? Fine. So in that case, what happens? What is the middle element when 28 is sent? 28 is somewhere here. It will find the root, right? So what is the middle element? 17. So 17 will become the root. Then to the left you will find 38. Yes or no? To the right you will find 28 and 48. So this 25, 26 will go to the left of 28, and this 29, 45 will go to the right of this, right? So this is how exactly, and this goes to the right of 48, right? So and this is going to be the left of 3, and this is going to be the right of 3, and this is going to be right of 8. This is how the tree is going to be formed. You can see after the corrections. Yes, sir. 17 occupied the root position because you need to split even this as well when you are inserting that, right? So at the end, you will get the tree like this. I hope this is clear. So you got now, how when you are trying to insert a node and falling under case 2, the nodes which are splitted there, taking the middle element onto its parent, making that parent also required to be splitted, has to be splitted. It means this concept is going to be recurrently applied until you reach the root. Okay, now this is an exercise. All of you can please note down your exercise. Construct a B tree taking these values. I hope all of you are noting down, right? 3, 7, 9, 23, 45, 1, 5, 14, 25, 24, 13, 11, 8, 19, 4, 31, 35, 56. Take these values and construct a B tree of order 5. You will get the result like this, okay? Anyway, now coming to removal. When you are trying to delete an element from B tree,
Once again put, sir, that exercise.
yeah, you can take the screenshot. Okay, please take the screenshot. You will get the correct values. Have you taken?
Yes, sir.
Yeah. So answer also you can probably take the screenshot. Anyway, now coming to removal, deleting a node from B tree. How do you delete a node? So again, to delete a node, delete a key value from a node, you need to first search for the node in which that particular key value is available, rather, right? So here again, you may find two cases, right? When you are trying to delete a key, fine. When you are trying to delete a key, when you are trying to delete a key, the node which you have identified, fine. Node which you have identified is having more than minimum key values. Okay, the node which you have identified to delete your key is having, let us say, is having more than minimum key values. This is the first case. So in this case, you can simply delete it because due to the deletion of your key, the node will not be left with less than minimum because the condition is as per the B tree properties, every node should have either minimum or to the maximum, but less than minimum it cannot have, and more than maximum it cannot have. Fine. So when you are trying to delete a key value from a node which is having more than minimum key values, then by deleting this key value, it will be left with minimum at least, rather. So it still satisfies the BT property. So there is no issue, rather, right? But case 2, that is when you are trying to delete a key value from a node, is having is having just the minimum key values, just the minimum key value. With the deletion of your key, it will be left with less than minimum key value. But in that case, it does not satisfy the B tree property. In that case, what is that you will do? You go with two sub cases, right? Two solutions. Solution one, right? Solution one, that is, you will look for a borrow. Okay, you will look for a borrow. Borrow a key value from its sibling. Borrow a key value. You can write down also, right? From its sibling. Sibling in the sense, to the left and right, it will have two siblings, right? Or it may have only one also in cases, in extreme cases. So solution one is borrow a key value from its sibling. But let us say if none of the sibling is in a position to lend you a key value, then solution two. Okay. So in solution two, what do you do? You will merge, right? You go for merging option. Merge node along with the parent key value. Merge node with its sibling, with its one of the sibling, with its one of its sibling. If it is having more, it means two. Otherwise, you go with one of its sibling along with parent key value, right? Got it. So case one is like, when the node is having more than minimum key values, simply delete it. Okay, case 2, if the node which you have identified in which your key is available to be deleted is having just the minimum key values, then you go with either of the solution. First, you look for the solution 1. Then if solution 1 is not possible, then only you go for solution 2. In solution 1, what do? You try to borrow a key value from one of its sibling. If one of its sibling is having more than minimum key values, then you can borrow a key value from it rather, right? Fine, that is one solution. It means if either left or right sibling having more than one key, having more than minimum key values, then you can borrow a key value from it, right? But let us say if none of the sibling is having more than or just having the minimum key values rather, right? It means it doesn't have more than minimum key. None of them is having more than minimum key values. It means that both of them are one of them, if it is only one, having just the minimum key values, then in that case you go for the solution 2. In that case, what you are trying to do is you are trying to merge that node with its sibling along with the parent key value. This is what the solution is. If you understand the cases, then probably implementation construction is not a difficult task. I hope this is clear to all of you. Shall I remove this? You please note it down. I hope you have noted down. That is what exactly here mentioned, right? If one of them has more than minimum number of key values, then we can promote one of its key towards parent and take the parent key into our lacking leaf. This is nothing but borrow procedure. If neither of them has more than minimum number of keys, then lacking leaf and one of its neighbor can be combined with the shared parent. This is said to be merging, right? Third one is borrowing. Fourth one is merging. So now let us look at here. Uh, what is happening when you are trying to delete, let us say, a key value from this particular one, you can simply delete it. When you are trying to delete 2, you can simply, because it is having more than minimum key value. What are the minimum key values that with order m a node should have is 2, right? So it's having 3, so you can simply delete it. Deleting 2 does not make this particular node left with less than minimum rather, right? So you can simply delete it. That is coming under case 1, right? You can simply delete it, right? Now when you are trying to delete 52, let us say, what happens when you are trying to delete 52? 52 is being deleted from the non-leaf node, that is from the root node you are trying to delete, right? In this case, what you do is you will promote its you know child value here and then you delete. Got it. So you can either go with the left one or right one. If you are taking the left of 52, then the last value of the left you should take. If you are going with the right, then you will take the first value of the right. So either of the solution is possible. Here the solution taken is taking 56 to be promoted. 56 you can promote here to its parent position, and you can delete this 52, right? This is one solution. Okay, so you can see 56 will go to the, yeah, 56 will go to the 52 position. This is how you have promoted. This is also a borrowing thing itself, right? This is coming under second case rather, right? When it is a non-leaf node, right? Anyway, now when you are trying to delete 72, you can see here. In this case, this particular node in which you are from which you are trying to delete 72, you can see is having just the minimum key values. Minimum is 2, right? So when you delete this, it will be left with less than minimum, which is not correct as per the BT property. In that case, what you have to do, you will go with the solution 1 or solution 2 of case 2, right? So under case 2, the solution 1 is borrowing a key value from its sibling. There is only one sibling left. There is no right sibling for this, right? So if you go to its sibling which is left here, that is only left where it is also having just the minimum key value. So can you borrow from this? No, this particular node cannot lend you a key value because it is also having just the minimum key values. In that case, you go with the solution 3. In solution 3, what happens? It will be merged along with the parent value. Parent value is 56. So along with the parent value, this entire thing is going to be merged. So when you are deleting 72 and get deleted, what happens? This particular node is going to be merged along with the sibling with the shade value of its parent rather, right? So you can see 31, 43, 56, and 69, right? So that's how exactly the tree is going to be formed now when it is, deleted. You can see here 72 when get deleted. What is happening? You are merging. This is the solution 2. This is the extreme solution that you are going to apply. Join back together, right? So you can see here 31, 43, 56, 69 to be attached to the right of 29, right? So when you are trying to delete, let us say 22, again in 22, you can see the node from which that 22 key value has to be deleted is having just the minimum key values, yes or no? So in that case, you first go for, this is case 2, falling under case 2, when it is minimum key values. So under case 2, you have solution 1. First you go with the solution 1. Whether you can borrow a key value. Yes, it is having two siblings, left sibling and right sibling. Left sibling cannot lend you a key value because it is also having just the minimum key values. But then right sibling is having more than minimum key values. Yes or no? More than minimum key values. It means you can borrow a key value from this. So when you borrow a key value, how does it going to be taken? Is nothing but this value will be promoted to the parent, and the parent value will be demoted to this particular child, and this 22 will be deleted. This is how the procedure is going to be done when you are borrowing a key value from its sibling, right? The sibling value will be promoted to the shared parent key, and that shared parent key will be demoted to the node from which the key is being deleted. Then you delete the key rather, right? So you can see here, after this is being done, you will find that the transform tree like this. Fine. You can see 29 comes down, right? So can you see this? All of the cases have been covered or not? Yes. So you take this as an exercise and try to delete the nodes after being constructed. 5A tree you construct using these values 3, 7, 9, 23, 45. Take the screenshot of this. Add further keys after you construct these trees. He is asking. So add these keys. This is as part of your assignment. I am rather giving this question and assignment also. So please solve this assignment. Then here he is asking you to delete this key value, delete the key values in this order, right? After the tree has been constructed with the above key values with the order 5. So I hope all of you have taken the screenshot. Is it clear to all of you? So the answer to the exercise is also I am giving you. This will be the exercise. At the end, you will get this particular result, rather, right? I hope this is clear to all of you. Yes, any doubt here?